Hi. In this video, which is going to be fairly short, we're going to work through some problems in symbolic matrix algebra. That is, manipulating expressions involving matrices and perhaps vectors, where we're representing them purely as sort of symbols, the idea of matrices and vectors, rather than as well-defined matrices that are filled with specific numbers, for example. We're going to address a number of true and false questions where we have two expressions on either side, and we want to ask, are they equivalent or not? As part of this, we also want to define what properties must the statement have, or must the elements in each statement have, in order to even make sense, for us even to be able to begin to evaluate it. I will present each problem one at a time, so there's no need for you to pause the video here, but I do recommend that as we present each problem, you pause, work through, assess whether it's true and false, and then resume to see the answer. Right. So the first question we're going to look at here involves a sum of matrices on either side. Let's begin with the question of what properties each statement has to make sense. In order for these problems to make any sense, we need to have matrices that are all of the same size. Why is this? This is because we have a sum of elements, or sum of matrices, a sum of matrices. Matrix addition only works when the matrices are of the same size. So we can consider this equation only if A, B, and C are in fact the same size. Otherwise, it's poorly defined. If they are all of the same size, the statement turns out to be true. How do we show that to be true? We just kind of apply the rules of manipulating these expressions. Matrix addition is associative, that we can move the order around, and commutative, that it doesn't really matter sort of the order of operation or the order of the matrices in the sum. And so we can sort of just move these around rather than computing C plus B first. We can add C and C together first, and then B and B together first, and then add A. These are equivalent expressions. And B plus B, of course, is the same as 2B, and C plus C is the same as 2C. We get, by a very simple manipulation, the same result that we have here. Okay. Next problem. Another problem involving sort of sums and differences of matrices on each side. Is this one true? Here, just as in the previous case, because we're dealing with sums and differences, the constraint on the problem for anything to even make sense is that A, B, and C are all of the same size. However, even if they are the same size, this equality turns out not to be true. How do we know this? We do the same thing. Expand this one first, so multiply out the two. Scalar multiplication and matrix addition are distributive, so 2A plus B is 2A plus 2B. Negative C minus 2B is negative C minus 2B. The 2B and the negative 2B cancel out, And what we're left with is 2a minus c. 2a minus c is not equal to 2a plus c because 2a minus c, go back there, 2a minus c, of course, would equal, if I can actually get the pen, this would in fact equal 2a minus 2c. So the expression is false. Move on to a question now that involves some powers of matrices and products of matrices. What properties does x and y have for this to make sense? Well, x and y have to be square matrices of the same size. Why? Powers of matrices only make sense for square matrices. If it is only a square matrix, if you think about the rule for how matrix multiplication works, what do we need for a product to matrix product to make sense? We need to have matching inner dimensions, right? For the product to make sense, we have to have these pieces match. Well, if we're talking about a vector, the same matrix on both sides, we're saying that the number of columns and the number of rows need to be the same. If we have something like x for both of them, then this n means we have to have an n here, and this n means we have to have an n here. We have a square matrix. We're also taking addition, which means they have to be of the same size for addition to make sense. Actually, the fact that we have an x times y here also means that they have to be of the same size, given that we know they're square. Okay, so we've established what needs to be true for the statement to make sense. Is it true or false? This expression turns out to be false. How do we know that? Again, we expand and simplify. X plus y squared simply means x plus y times x plus y. Matrix multiplication distributes into matrix addition. That means that when we do this, we get x times x plus x times y plus y times x plus y times y, as we have here. Right? X times x, of course, is equal to x squared. Y times y is equal to y squared. For matrices, matrix multiplication is generally not commutative. X, y, as a general rule, is not equal to yx. There are some pairs of matrices where this is true, but it is not generally true for arbitrary matrices. Because that equality does not hold true, we cannot combine these two terms into a 2xy, and these are not equal. This is where matrices behave differently than an analogous expression for scalars. If x and y were scalars, this would be a perfectly true expression. All right. One last example where we now combine addition and subtraction of matrices, multiplication and powers of matrices, and we add in the transpose. All right. Is this expression true or false? And what does properties to x and y have to have? Well, once again, we have powers of matrices. Powers of matrices are only well defined if they are square matrices. So x and y have to be square. Should note that when you take the transpose of a square matrix, it is also a square matrix of the same size. So the fact that this is x transpose squared and y transpose squared doesn't change this requirement. We're also taking sums of x and y and a product here of x and y and here. So x and y also have to be of the same size. If they are of the same size and square, is the statement true? It turns out that it is. How do we evaluate that? How do we determine that? Once again, we do the expansion and simplify. First thing we are going to do is we're going to distribute the transpose through these expressions. We remember that when we do this, when we distribute the transpose through a product, we have to change the order. Take the transpose of each, multiply them together, and change the order. So what does this mean? X plus y times x minus y transpose becomes x minus y transpose times x plus y transpose. Swapping the order with respect to here. X, y, all transpose becomes y transpose x transpose. We then distribute the transpose through these sums and differences. That happens just very simply. We simply distribute the transpose into this expression. X minus y transpose is x transpose minus y transpose. X plus y transpose is x transpose plus y transpose. We won't do anything more with this term. At this point, there's not really much to work with there. We then apply this matrix product just as we did in the last example using the distributive property of matrix multiplication. X transpose times x transpose plus x transpose times y transpose minus y transpose times x transpose minus y transpose times y transpose. This should actually, there's a little typo there that I will fix in the slides. This should be a negative, not a positive. It's correct in the next piece. And so that's that expansion. And then we have this additional y transpose, x transpose piece that we had there. We then see that we have x transpose becomes x transpose square. X transpose y transpose stays as it is. Negative y transpose x transpose plus y transpose x transpose. This gives us 0, which disappears, minus y transpose squared. This is the expression we have, which was the right-hand side here. We have a true statement. These examples just give us a little bit of a flavor for the kind of manipulations we can do with sort of symbolic expressions of matrices. We're not going to be spending a lot of time in the class on this kind of manipulation, but it is important to have a basic comfort with it. There are some places, there are some problems where this kind of manipulation is important in order to translate a problem into a form that we're able to solve. Right? this is the end of our sort of videos for the second unit. In future units, we will be digging much more into the methods of linear algebra. Thank you and goodbye.